Let's design a hotel reservation system similar to Booking.com or Airbnb, which is a typical system design interview problem. The mistake that most developers make here is when they ask to design such a system, they treat it like a typical CRUD application with some caching and replication for the availability. But that's not the correct way to think about it. For instance, one of the problems that you might have is a moment when two users are trying to book the last room available at the same time, and you try your simple select then insert approach, which creates the double booking problem. So you end up charging 2 credit cards for one room, and now you're dealing with refunds, with angry customers, and a system that cannot be trusted for the next time. That's why hotel reservation systems are hard, because they also test the exact skills that separate mid-level developers from seniors. Things like handling concurrency without breaking it under heavy load, keeping the data consistent across multiple systems, and also designing for failure in case something goes wrong in parts of the system. And it's not about memorizing these patterns, but rather understanding the actual problems that might occur, what are the solutions to those, and what are the trade-offs between those solutions. So we're going to design this system in 4 simple steps. First, we will gather the design requirements, estimate the storage and queries per second, transactions per second, and anything else that we need for designing the system. Then we'll get into the basic high-level design, including the API design, database schema, reservation flows, and so on. And in the third step, we will scale the system to handle 1000 queries per second and 17 transactions per second, which are the numbers that are close to the real Booking.com scale. And then we will handle the failures under heavy load and discuss the system recovery whenever some things or some parts of the system fail. So if you're tired of system design explanations that skip the hard part and only give you the surface level, then this one is for you. Let's start with the first step, which is the design requirements. In such challenges, we usually follow a framework to come up with the solution. And the very first step is always to ask clarifying questions to lock in the scope that we are going to design, and then also about functional and non-functional requirements. So let's start with the clarifying questions that we might have. For example, one of the questions can be about the payments, which is, are we going to allow them to pay at the platform, or it is going to be a payment in check-in? And this will let us know whether we support payments in the platform or not. For this one, let's say yes, so we are going to allow them to pay at the platform, which means we need to have some sort of payment system inside. Another question can be about booking channels. So is this a website only web app where they are going to book the hotels, or we also support the mobile app, which might have different rates and different pricings? So let's say we are going to design both, like web version and mobile version of this application. Then about cancellations and overbooking. So do we support cancellations of the reservations and also overbooking? Because hotels typically allow some sort of overbooking, taking into account that there might be some cancellations. So if they are getting, let's say, 10 bookings per month, then out of these, like 2 or 3 are going to be canceled. So they allow users to also overbook because of the cancellations. Once they get some cancellations, the room is free now, so they will allow overbooking as well. Then about the dynamic pricing. So are the prices fixed, or the price changes based on the demand and the dates? And for this, let's say we are going to have dynamic pricing whenever the demand is higher. So it's, let's say, Christmas time, which is around now. We are going to increase the prices. For example, this room where I'm recording from, it was triple of the price as in usual, because that is the Christmas time. So they are going to increase the numbers. And similar to that, any other popular dates that people are reserving, we are going to increase the prices based on the demand that we are getting. Then we can get to the functional requirements. So one question might be about the hotel management. Are we going to support the admin panel, like adding, updating, removing hotels, or we are only focused on the user part? Admin panels might be included in this, but the core functionality evolves usually around the users, which are booking the hotels, canceling them. Let's say we are going to also support some sort of admin panel in this system. Then we get to the search and discovery questions, like what are the core functionalities we are going to support? And a way you can think about this is, what are the functionalities that if we remove from Booking.com, it doesn't become booking.com anymore. This might be a good approach for identifying what are the core functionalities. For example, if users are not able to search hotels by location, then it becomes some sort of useless application, right? So of course, one of the core functionalities we will support is that users need to be able to search by location, by dates, by guest number, price range, and some other filters that we might set. Then about the reservation flow, how usually it happens is users book the rooms, then they view the reservations, they should be able to cancel the bookings because we also clarified it above. And also the system should prevent double bookings. This is one of the challenges we need to identify here so that we also solve it in the next steps. Then about the payment processing, since we clarified that we are going to support payments in the app, then we need to integrate some sort of payment processing like Stripe, PayPal or something else. And optionally, it might also include notifications, so sending confirmations for bookings or cancellations or payments to both user and the admins, brokers who are uploading these hotels. Then we get into the non-functional requirements, which are more about the consistency, load, and latency that we are going to support. Let's start with the consistency. We are going to have strong consistency because two users shouldn't be able to book the same room for the same dates. That is non-negotiable. But whenever they are searching or discovering the rooms, there the eventual consistency is fine. And you will see why also when we get to the designing phase. Then about the concurrency, so we need to handle thousands of users trying to book the same hotel simultaneously and without it breaking the system. Also about the latency, we need to provide low latency, so search results should appear under 500 milliseconds and booking confirmations are fine if they are handled between 2 or 3 seconds. You should also clarify the availability and scale. Let's say for availability, we are going to support the 3 nines uptime. And when it comes to scale, we need to be able to scale this horizontally without redesigning the system from scratch in the future. Once we gather the design requirements, we can move on to the estimation of data and capacity, and after that we can start designing the system. Now, when it comes to the data estimation, the most important things we are interested here is the queries per second that are going to happen in the system and also transactions per second, which are the writes to the database when users are booking hotels. So in this kind of system, you can think about it as this funnel here. The users that come to the platform are at the top here. So these are the users who are viewing the hotel room. This is the 100% of the traffic somewhere here. And then next we have out of these users, probably like only 10% will go into browsing the hotels and searching for some good matches and booking the hotel. So that will be the second layer here. And then third, we will have the reservations. So only out of these, only the 10% are actually going to book anything because most of the visitors are tire kickers. They are not looking to book anything. They are just browsing, but we still need to design the systems for them because they are also going to increase the queries per second that are happening in the system. So based on this, there are two ways for us to calculate the load. One approach is, let's say, to take a look at the booking.com, and you can use some sort of extension like SimilarWeb to see the traffic that it's getting per month. For example, this month it got 500 million visitors in the website. That means that 500 million users were browsing the system this month, so at the top. And then you can start calculating it down based on this to see also the transactions per second and what are the queries per second based on this load. And the other way is the bottom-up approach, which is to get the number of reservations per year, let's say. And for booking.com, that is 1.1 billion reservations per year. And then we can calculate this upwards. So starting from here, how many visits we get per month or per second to the platform. And we will also be able to calculate the transactions per second because we have the number for the year reservation. So each of these numbers is fine. You just need to get one of them from the interviewer and then you can start the calculations. And also take into account that these numbers are also rough estimates. So you might get these numbers exactly to calculate, or you might get just the visits per year and the bookings per year, and you should be able to calculate it after that. The other important metric that we need is the average stay. So what is the average stay that users are booking the hotels? Let's just say 2 or 3 nights per booking. So let's go with the 2 nights per booking, and then we will be able to calculate the rest. So let's start with the daily reservations. We have the number of bookings per year, which is 1.5 billion rooms per night. Let's just start with this approach. Then we can divide this by the nights per booking, and that comes down to 550 million bookings per year. Because this is the room nights in total, this is not the bookings. So we need to divide this by the nights per booking to get the actual number that we are getting booked per year. Then we can divide this by 365, which is the days in the year, and we'll get the number of bookings per day, which is 1.5 million. And after that, we can divide the 1.5 million by the seconds per day, which is 86,400. And that means that we are getting 17 bookings per second, which is the transactions per second that we are going to support in the database. Then when it comes to the traffic funnel part and the reads, as you saw with SimilarWeb, we are getting something like 500 million visits per month in the booking.com with about 8 pages per visit, which means that on each visit, the users are going to browse around 8 pages before they leave the website. Based on this, we can first get the visits per day, and we can get that by dividing the monthly traffic with 30, which are the days in the month, and we'll get to 17 million visits per day. After that, we can get the visits per second. So if we divide that by the seconds in the day, we will get 200 visits per second to our website. And if we assume that they are going to browse around 8 pages per visit before they leave, let's say that it comes down to 5 backend reads per visit, which can be things like search queries, availability checks. So we need to just increase this number by multiplying it with the 5, and we'll get around 1000 read requests per second. And based on these calculations, we can clearly see that this is going to be a strong read-heavy system, because we have 1000 QPS queries per second that we need to support, and only 17 TPS, which are the transactions per second that we will get. So our challenge here will be to optimize the architecture for reads while still keeping the writes consistent to avoid the double booking problem. These are the core numbers we need to start designing the system, and then the rest we can look at while designing the API database, and if there are any more things that we need, it's fine to calculate those there, but at least we need to get the main things that we need before starting with the high-level design. After the scale and data size calculations, we can now design an architecture that fits these numbers. So we can start by using a service-oriented architecture with clear boundaries, but also keep the tightly coupled data in the same database. So as a starting point, let's say we have the mobile app or the web app where users are browsing these hotels and making the reservations. We'll use CDN in front here for the static assets like rendering the images, media files, also the JavaScript content and the hotel images. Then we have an API gateway, which will be the single entry point to our application. This is where we will handle the authentication, the rate limiting, and also routing the requests between all the services that we have. It can also serve as a load balancer across service instances. So if you have multiple instances of hotel service, let's say, this API gateway can serve as a load balancer and route the traffic between the instance 1 and instance 2. When it comes to services, we can separate this with boundaries for hotel service. This is where we will have hotel and room information, mostly static and heavy cacheable service. An important service here is a reservation service. This will handle the booking logic, inventory checks, reservation creation and cancellation. And this is also where concurrency will be handled in the application. Next, we have a rate service. This will be for room pricing by date, because depending on the date and when you book the hotel, the price will be different. So this will be applying dynamic pricing based on the demand of the rooms. To integrate the payment gateways, we will also need a payment service that will implement, let's say, Stripe payments, PayPal payments, Apple Pay, Google Pay, and other payment providers. And we also have a notification service that talks with the reservation service and with the payment service. This is what sends the emails and push notifications. For the data layer, initially, we can start by using some sort of SQL database like PostgreSQL, primarily because we will need the ACID guarantees, and this will be also useful for the transaction store. And we will be using many transactions, so we need the consistency of SQL databases. That's why we go with SQL in this case. We also need some sort of caching like Redis for the data that doesn't change that often. But we can also improve this a bit further. So first of all, if we think about the scale of the reads that we will have, which is around 1000 queries per second, PostgreSQL database won't be able to handle that load. So we need to give some sort of solution to this. For such situations, tools like Elasticsearch are a good solution for handling the massive scale for the search. So we will introduce a search service that will be responsible for retrieving the hotels by the filters that are set on the front end. And Elasticsearch will handle the full text-based search on hotel names and descriptions. Also, it will be able to filter hotels, let's say within 5 kilometers of location or within some range to that location that is set. And it will be able to filter by the price, range, ratings, and any other filters that we need. The thing with Elasticsearch is that it's way faster than the PostgreSQL database that we will use, let's say for listing the hotels. And also it is eventually consistent, meaning that eventually it gets updated with the database and gets the latest data in the Elasticsearch and indexes everything properly to be able to search quickly based on locations or based on the price range and any other filters. We can also decouple the services a bit. Another approach is to use different databases for each microservices. Like for the payment service, we can have payment database. For the hotel service, we can have hotel database. And we'll discuss what's the pros and cons of this. But to also decouple them, we can introduce a message queue that will be responsible, for instance, for payments. Whenever a payment is processed in a payment service, we will process that and publish a message in a Kafka RabbitMQ or some other messaging queue. And this will first of all send email push notification to the user or to the owner as well as an email or as an in-app notification that the payment was successful and the hotel is reserved. And it will also update the availability, meaning the status of the hotel. So it will push that to the search service, which will update it in the Elasticsearch. And that is, again, getting eventually consistent. So right after the payment, maybe if users search, they will still see that hotel available, but they won't be able to book it because we are using the hotel database to double check whether it's really available or not. And eventually, after some time, this will be persisted with the database and it will have the same data as the PostgreSQL database. Next, when it comes to choosing whether all these services will be like microservices or a single monolith, or they can also be pragmatic microservices. For example, in our case, a single monolith would simplify the transactions, but it will become hard to scale and deploy independently because if many developers, let's say hundreds of developers are working on this single monolith, then it becomes very hard to deploy independently and work on things without stepping on each other. Another approach is full microservices like this, where you have rate service, notification service, and so on, with separate databases, which will introduce distributed transactions and consistency problems that don't exist at the monolith level. That is because each service, as you can see, like hotel service owns its own database, reservation service owns its own database. So another approach is to keep the tightly coupled data together in one database and share it between the services. For example, in our case, the reservations and the hotel databases can be kept together. This will let us to use the local ACID transactions instead of the distributed transactions, and we will have a service level separation at the application layer, but we will still have the shared data for tightly coupled entities. After you agree on the high-level design, the next step is the API and database design, and you can start with API design, then database, or vice versa, whichever way it's easier for you to talk about the flow. So in our case, let's start with the API design. We will use Restful APIs for all the operations because that is what makes sense in this kind of system. Although, as you can see here, the front end directly makes calls to Hotel API, to other APIs as well that we have. Maybe sometimes it will make calls to Reservation API. Another approach here, a very common one, is when you have multiple microservices. Usually you would use a GraphQL layer in front of the front end. So front end will only make requests to the GraphQL, and it also will know the schema based on the GraphQL schema. And then the GraphQL layer will be responsible for making calls to all these services that you have behind the scenes. So it kind of extracts away the complexity and the routing between these services. But to keep it simple on the diagram, let's just assume that front end makes the calls directly. So we have here admins who are listing the properties. We have users who are browsing the hotels and making reservations. And we have the front-end app, which is either a mobile app or the web version. The very first step for admins is they need to be able to log in to be able to use the features for the admins, while users can be browsing the hotels without being logged in. But whenever it comes the point for the reservation, they need to also create an account or log in. For listing the available hotels, we will make a GET request to /hotels with any necessary filters that the user sets, and we will get the available hotels. And then if they want to browse a specific hotel, then we will make a request, same GET request to /hotels /specific ID of the hotel, which will return us the hotel that has that specific ID. Now, how it will happen behind the scenes is Hotel API will fetch the hotel details from the database. So for specific hotel, we can also read this from the PostgreSQL database. But in the initial call where we are making a request to /hotels, that is where we will be using the Elasticsearch to quickly filter based on the filters that are set on the front end. And at this step for a single hotel, we just basically forward the hotel details to the front end, and then front end is responsible for parsing and showing the details in the page. For admins who want to add a new hotel, they will need to make a post request to /hotels endpoint. And this is where we will insert it into the SQL first. And then once we get a successful insert, we will just forward the 201 status that the hotel is created, and later this will be eventually persisted with the Elasticsearch database. But we will show the confirmation at this step to the admin that the hotel has been created. And similarly, if they want to update the hotel information and they make some edits, we can make a put or patch request to hotels /ID of that hotel, and again update it in the database, get the update result and send the confirmation and show it for the admin. A similar flow for removing hotels, again a delete request in this case to /hotels /ID of that hotel. We remove it from the database and we show it to the user, and later this will be removed from the Elasticsearch. And within hotels we will also have rooms because one hotel has many available rooms. We will treat them as a sub-resource. So under hotels and specific ID of the hotel, we will have /rooms first of all, which will give you all the rooms that are available under this hotel. And to fetch the specific hotel, you can make a request to /ID and get more details from that hotel, which will again fetch from the database, and then you will forward it to the client. And basically, here we are just repeating whatever we have for the hotels, but for the rooms. So if you want to add a room, you will make a request to post /ID of the hotel /the rooms. this is again following the general RESTful principles. We will insert the room in the database and provide with a successful response. Of course, you need to also handle the failures whenever something goes wrong, showing the error on why something went wrong in the API. But when talking about the happy paths, or at least the available endpoints, these are what we will have. We will also have a put endpoint, which is for editing the room type to again /rooms. In this case, we need to provide an ID because we are not creating a new one, but we are editing one. So we need to specify which ID is that room that we are editing. And same goes for deleting, the same URL as we have for the put, but in this case, the method will be delete, which will remove the listing from the hotel. Then for the reservations, this is where we will make requests to the reservation service. Let's say a user wants to see their reservation history. We need to provide an endpoint here to fetch the reservations. So a get request to /reservations, which will read it from the SQL database and then forward the response to the client. Then they want to see, let's say, a reservation details and the invoice that they paid. So that is where we will have the get endpoint to /reservations/ID of a single reservation, which will fetch the details from the database. We will get the details back and we will forward it to the front end and we will parse and show it to the client. Next, when creating new reservations, they will fill the reservation form in the front end. Then we will send these form details in a post request to reservations. One important thing here is that at this step, we can already prevent double booking for single user. There are two scenarios, like one user can try to double click or click the same reservation room twice. So that's one scenario which we can handle here. The other one is that two users can try to book the same room twice. We will handle that in the later step. But at this step, for example, one solution is we can include a key like a reservation ID, and this will be generated on the front end, which will be used to prevent double bookings when user clicks submit multiple times. So if we have the hotel ID and the room ID that this user is trying to book, basically we generate a reservation ID once, and then if they try to double book it, like book it again, we will be able to catch it in the database and see that the reservation ID is the same. So we will block them from making a request, or we can even do it on the front end side. Another solution is you can also do it on the backend side. For example, when they make a request to book something, you can combine the hotel ID in combination with room ID, the user ID who tries to book this, and also the date or some sort of timestamp. Why? Because in the future, this user might try to book it again. And if you just use these in combination, then basically you are blocking them to make a future reservation on the same hotel. So you can also use these in combination to generate some sort of hash. And whenever the hash matches from the database, then you block them from making the reservation. But this is way simpler solution on the front-end side to just generate some sort of UUID for the reservation ID if you are talking only about a single user and preventing them from booking again. Then this is a very lightweight solution and way simpler than inserting this hash into the database and checking it every time in the backend. So here we will first check for existing reservation ID. If it's not found, then we will insert a new reservation. So assuming it's not a double booking and we get the reservation confirmation, we will just show them the confirmation, and behind the scenes the Kafka message will be published and it will send the notifications to the user and to the owner of the hotel. But if it's a duplicate reservation attempt, then they will make a request and this will contain that reservation ID. So we will check for the existing reservation ID, and if a transaction like that already happened and we have the reservation and it already exists, then we will return the existing reservation and show it to the user that this is already reserved. Similarly, they might want to either cancel the reservation or change the dates of the reservation. So we need to provide endpoints for that as well. In case of canceling, it will be a delete request to reservations/ID of that reservation. And in the database, we just need to check whether it's allowed to cancel, because if they try to cancel a week before the appointment, then it's allowed, or if they try to cancel it last minute, then it's probably not allowed. So in case it is allowed, we will just send the confirmation. Otherwise, we will send a response that we cannot delete the reservation, meaning we cannot cancel it, and show the options to the user. Similar to this, you might also have edit reservation with put request, which will update the dates. For example, if plans have changed and you want to update the dates, then we will make a put request to that ID reservation. Let's also see how the search will happen. So another service we will have for this is the search service, which will be connected with the Elasticsearch. So let's say user sets the filters like the location where they want this hotel to be located at, the dates, start and end date, and so on. And we make a GET request to /search. These will include the location, the check-in, check-out time, how many guests you have, how many beds you want, the price range, and any other necessary filters. This is where we will query the available hotels and room types. But an important thing is we will query this from the Elasticsearch. In this case, we won't query it from the database because it's way faster, and that's the point of us setting up Elasticsearch, so that we can quickly return the search results. And this will return the available hotels within the range of that location and within that price range and the check-in, check-out time. And front-end will be parsing and showing it to the users. Next, let's move on to the data models and the database design. One important thing here is that you book the room type and not the specific room. So you book a specific type of room, like is it a double queen bed or something else, and not a specific room, because the room numbers are assigned at the check-in and not here. But let's start from the hotels because it will make more sense this way. So we will have, of course, the ID of the hotel, which is the indicator of the unique ID for this hotel. It can have a name, address, location, description, and so on. Now, there might be also hotels that are under the same brand name. In this case, you can either have the same hotel name but different hotel IDs. So it will be a different hotel LLC in US, let's say. It will be a different hotel LLC in Europe. The name will be the same, but the ID will be different. Or you can use a helper table like hotel groups and then group them under a brand name if there are brands that have multiple hotels at different locations. Then the important part is the room type that we need to have. So the ID of the room type, its name, description, and then how many people it can serve, the ID of the hotel, which connects back to the hotel. So one hotel can have multiple room types, and this is a one-to-many relation. Then each room type is also connected with room type rate, because each of these rooms will have a different rate. Let's say we have a room which is the basic package. And as a basic example, let's say it costs $100 per day. So this is the basic package. Then you can have a room with a better view. In this case, it will be something like $150 per day. You can have a hotel room with breakfast included, and that will be something like 200 and so on. So that is the reason why we have these room type rates, because for different room type, we will have a different rate that will be multiplied by the base number that we have here. And this is again one-to-many relation, because one room type can have multiple room type rates. Then this is where we have the actual rooms. So what is the room ID? This is the exact room that we are going to assign at the check-in. Then it will have some more metadata like floor, number, whether it's available. This is the important part that will be tracking the status. And this is also what we are reading when checking the availability. And the room type ID, which again refers back to the room type. So one room type can have multiple rooms in it. which means you can have a hotel. Under that hotel, you have multiple room types, like you have, let's say, the basic type. And in the basic type, you might have 3 rooms available that are all basic rooms. This also connects to the hotel ID so that you can determine which exact hotel this belongs to. You could also join it with the room types and then get the hotel ID like that, but it will be helpful for us to have the hotel ID here. So this will be like which hotel does it belong to, the room that we are assigning at the check-in. Next, we will have the room type inventory. Inventory is tracked per hotel, per room type and day, so not the physical room. This will enable us to have bulk availability updates, also scalable pricing and search, and it will be simple overbooking logic because we will also support overbooking considering the cancellations that we will have in the rooms. So here we will track the room ID type, the hotel ID, and this is again one-to-many relationships between the room type and between the hotel. And some more things like the date, the total inventory, total reserved, and so on. Another important table here is the reservations, because once user selects the hotel room, specific room, we will need to reserve it. So we will track the reservation ID, which we will link later to the transactions. We will have the room type ID. This refers to the room types table. We will have the exact hotel ID where they booked this, which refers to the hotels table. The guest ID, which is the user who booked it. So for that we will have a guests table, and we can additionally have, let's say, admins or brokers table, which will be the users who are publishing these rooms. So here the most important thing for us is the guest ID, the first name, last name, email, and so on. So we will connect it with one-to-many relationship here, because one user, one guest can reserve multiple hotels. So that's why it is one-to-many. Then some more metadata like start date, end date, status, whether it's reserved, whether it's canceled, and so on. And another important piece here is that we will separate transactions into a separate table. The reason here is that, let's say you reserve the hotel first. So first the status is reserved. Then the user can either change their mind, and here they can either cancel the reservation, or they might request a change in the date. So they might request to change the start and end date. In the second case, there will be a price difference that they will either have to pay or we have to refund them. So that will be another transaction, right? And that's why one reservation can have multiple transactions. So the first transaction is when they reserve, and then the second one is when they decide to change the dates, let's say, and update the reservation. They make another payment here, which is a second transaction. Or if they decide to cancel, that is another transaction where the amount in this case is minus, so we are refunding the payment, but that is still a separate transaction, and that's why we will have separate transactions table where we will track the ID of transaction, which reservation does this belong to, the type of the transaction like refund, change, or the new transaction, and the amount, which can be both positive and a negative number. With this schema, the room type inventory table has one row per hotel, room type, and date combination. We will pre-populate this for the next 2 years, and then a daily cron job can add new dates as the time moves forward. So we can also take a look at some example data here. We'll have the hotel ID where these room types belong to. Then the room type ID, let's say these 3 rooms are from the same type, like the basic type. Dates where we are checking these for, like December 15, 16, 17, and so on. And then we will see the total inventory and also total reserve, which will give us an idea on how many rooms we have available. When checking the availability, if you're using the SQL database, let's say, for December 23 to 27, we will select the date, total inventory, and total reserved, which is this column here, and then the total inventory, which is the available. We will select it from the room type inventory, where the hotel ID and room type ID match, and we will set the date to be between the range that we want to. This will give us the total reserved and total inventory. And by using this, we can check that if the total reserve plus rooms to book is still less than equal to the total inventory, then we allow the booking, which means if, let's say here we have 100 and here we have 92, so we still have 8 rooms available, and if user is trying to book just one room, that will be 92 plus 1, and we are checking this against 100, so the condition will be true and we will allow the booking. And coming back to the initial requirements, since we allow, let's say, 10% overbooking or whatever that number is, we can include that overbooking factor here. Let's say if we allow 10% overbooking, then we will allow 10%, like set the 10% here, meaning if we have 100 total inventory available, then we will allow them to book up to 110 rooms, because we know that the other 10 will probably be cancelled until the date of the reservation. And lastly, let's also discuss why we move with relational database. In this case, we kind of touched on this, but let's get a bit deeper in why we choose this. So first, the most important thing we need here is the ACID guarantees, and specifically the consistency of SQL databases. This is important for us for preventing double booking issues, which we will handle soon. From the calculations, we can also see that this is a very read-heavy system. So relational databases handle these kind of reads well, and we can always combine it with Elasticsearch for scaling it. But with 1000 reads queries per second versus 17 writes per second, this clearly shows that we need to go with an SQL database here in combination with the consistency factor that we need from the ACID. And then the relationships are more clear this way, like between rooms, hotels, the room types, reservations, transactions, and so on. And we'll need to make complex queries to check the availability of the rooms or make multiple joins for inventory with pricing, filter by dates, aggregate totals, and so on. So SQL will handle this well as well. We also need to handle the concurrency. We already discussed the first scenario where the same user is trying to book the same room twice. And the solution here is just to have that reservation key. So any second request will get duplicate key error and we will return the existing reservation. So that's the simple one that we can solve. But then the second scenario is we have two different users who are trying to book the same room type, which is only one spot left for that hotel. And if you know about the SQL isolation layers, by default this will be read committed, and concurrency bugs still happen at read committed isolation layer, which means that you only see data after other transactions commit. But there is a gap between when you read, like check the availability, and when you write, which is you book the room. And in that gap, you might have two different transactions happening, like user A reads the total reserved. He sees that one room is available because the total is 100. And user B also reads and sees that there are 99 rooms reserved and 100 available, which means that there is one available. So for both of them, the checks shows successful, like the condition is true, which means that we allow them to proceed with the booking. So read committed by itself is unsafe for bookings because two transactions can both read valid data, pass checks, and then overwrite each other. And that's exactly how double bookings happen. As a solution to this, we have two main approaches in this case. The next phase is scaling the system, because as much as we designed it with the microservice architecture and talked about the numbers that we are going to handle, we still need to scale the database, talk about the caching strategy, optimizing the Elasticsearch queries, and more. From this point forward, this part is exclusively for the members in my mentorship program. If you'd like to get access to this plus more systems and participate in discussions live and get to a point where you can confidently design such systems from scratch and not just copy paste or follow what senior engineers do, then there is a link in the description which you can check out for more details to become a member in the program. See you there.